Alright, so we're going to start with a review of ideal gas behavior. I've covered this in your freshman chemistry courses, and the reason we're interested in ideal gas behavior is because that's the simplest kind of system that we can apply the thermodynamics principles that we're going to be covering in this class. Okay, so ideal gas. To describe a gas, okay, the ideal gas equation is a very neat equation because it summarizes the behavior of gases when the pressure approaches zero. So under very low pressures, this equation, PV equals nRT, the ideal gas equation, pretty much summarizes all gases, the behavior of all gases. Under ordinary conditions, like room temperature, 1 atmosphere pressure, if you use this equation to do calculations, you'll probably be in error by about 1%. So that's a pretty good equation. Okay, so in this equation, P is pressure, V is volume, N is the number of moles of gas particles, R is a constant, and the temperature is in Kelvin. Okay. Now, the unit for R depends on what units you use for your pressure, volume, and temperature is in Kelvin. So first of all, let's talk about pressure. Pressure is defined as force per unit area. Okay, so let's just talk about the pressure due to a column of liquid. Let's say you have a column of liquid that's 760 centimeters high. Okay, a column of mercury. And that's 76 centimeters high. Okay, if you're at the bottom of that column, so if that column is on top of you, how much pressure would you feel? So what's the force that the column will exert on you? That's just the weight of the column, right? So the pressure that you feel, this is the force due to the column divided by the area of the column, cross-sectional area. Okay. And the force that you feel is just the weight of the mercury column. And weight is just mass times acceleration due to gravity. So the pressure that you feel is mass times acceleration due to gravity divided by the area. Okay? Now, the density of a liquid is mass over volume, right? So the mass is just density times volume. So I can replace this mass here by density times volume. All right? And the volume is just the area times the height of the column. So if this is the cross-sectional area down here, you multiply that by the height of the column. Area times height is volume, right? So that means if I divide volume by area, I'm just going to get my height. So if I rearrange this equation right here, I'm going to put together volume over area. I can replace that by the height. So the pressure due to a column of liquid would be, so if you're at the bottom of that column of liquid, the pressure that you'll feel will just be equal to the density of that liquid multiplied by the acceleration due to gravity multiplied by the height of the liquid. So let's calculate that. So pressure, what's the density of mercury? Mercury has a density of 13.6 grams per cubic centimeters, or 13.6 times 10 to the third, okay? 1 gram per milliliter, or 1 gram per cubic centimeter, is equivalent to 1,000 kilograms per cubic meter. You should be able to do that conversion. That's equivalence. So let's put that in terms of SI units. So 13.6, your density is 13.6 times 10 to the third kilograms per cubic meter. That's your density. What's the acceleration due to gravity? 9.80 meters per second squared. And what's our height? 0.76 centimeters. Okay. And that should give you, okay, I'm sorry, meters, that's meters. So 0.76 meters because that's 76 centimeters. And if you calculate that, that gives you how much? We'll just do 2 sig figs. That's 0.76 there. So let me see. I can pull up MathCAD. Okay. 13.6. Got a big font. 6 kilogram. Oops. What is it? Per cubic meter, right? Times 9.80 times meters per second squared times our height is 0.76 meters, and that gives us 1.01 times 0.293 pascals. Oh, I forgot, there's a times 10 to the third here, right? 13.6 times 10 to the third. So 1.013 times 10 to the fifth pascals. Pascal is your unit of pressure. Okay? Let's say I want that in terms of newtons. Newton is a unit of force, right? So what will happen here? It will tell me the unit is Newton per square meter. So force per unit area. Okay? So that's your unit for the SI unit for pressure is a Pascal. It's a Newton per square meter. So a column of mercury that is 76 centimeters tall would exert a pressure of 1.01 times 10 to the fifth Pascal. Okay, so this comes out to 1.01 times 10 to the fifth Pascal. Now, if you're only doing 2 sig figs, then that's just going to be 1.0 times 10 to the fifth Pascal. Now, if you treat 0.76 as exact, then the exact equivalence of 76 centimeters of mercury is 1.01325 times 10 to the fifth Pascal. Now, centimeter of mercury, you'll notice pressure is directly proportional to the height, right? So the taller the column, the higher the pressure. So the height of a column of mercury can be used as a unit of pressure. So you can use centimeters of mercury or millimeters of mercury. So 76 centimeters of mercury, that much pressure is equivalent to 1.01325 times 10 to the fifth Pascal. So that's the more precise value. And that's what we call 1 atmosphere. Okay, so a column of mercury that's 76 centimeters high is equivalent to 1 atmosphere of pressure. Okay? So the SI unit for pressure is a Pascal. It's a newtons per square meter. And of course, you're familiar with the traditional unit that we use, atmosphere. Torr, in honor of Torricelli, is equivalent to 1 millimeter of mercury. Okay, so 1 atmosphere is 760 torrs. It's 760 millimeters of mercury, or 76 centimeters of mercury. Now, a unit that is gaining popularity because of the transition to SI is the bar. And the reason it's popular is because a bar is very close to 1 atmosphere. Okay, 10 to the fifth Pascal is 1 bar. If you remember, what did we have earlier? We said that 76 centimeters of mercury, 1 atmosphere, is about 10 to the fifth Pascal. So a bar is in fact defined to be exactly 10 to the fifth Pascal. So you can say that 1 atmosphere is 1.01325 bar. Okay, 10 to the fifth Pascal is a bar. A millibar would be 1,000, 1/1000 of a bar. Okay, so if you look at news reports about hurricanes, for example, you'll notice they now give those the pressure in the eye of the hurricane in terms of millibars. Okay. All right, let's calculate the pressure due to a 1-meter column of mercury in pascals, atmosphere, torr, and millimeters of mercury. You should be able to do that, huh? So what would we need to do the conversion? 1.00 meters of mercury. What's the conversion from mercury to Pascal? Millimeters of mercury. One meter of mercury is 1,000 millimeters, right? And so that gives you millimeters of mercury. And then if you want to change that to Pascal, 1 Pascal is 1.01325 times 10 to the 5th pascals. I don't have room here. I can multiply that by 1.01325 times 10 to the 5th pascals, equivalent to 760 millimeters of mercury. Right. So it's a simple conversion problem. All right. What if you have a vertical column of water that's 760 millimeters long? What would be the pressure due to that column of water? Well, your water is not as dense as mercury. The density of water is only 1.00 grams per mil. Mercury is 13.6. So this is going to be 13.6 times less than the pressure due to a column of mercury, same length of mercury, right? So you can use millimeters of water as a unit of pressure. So what would be the equivalent then? You would say that 1 millimeter of mercury would be equivalent to 13.6 millimeters of water. You could use the conversion factor that 1 millimeter of mercury is equivalent to 13.6 millimeters of mercury. Or if you want to do it the hard way, you can go back to the formula. Pressure is density times acceleration due to gravity times h. In fact, you can show that. Okay. The pressure, if pressure is density times g times h, right? So if you have the same pressure for mercury and water, so I'm going to call this density D1 and H1 for mercury. If that's the same as the pressure due to a column of water, so D2, G, H2, where D2 is the density of water, H2 is the height of the water column, then you can see if you have two columns, a column of mercury and a column of water that have the same pressure, how are the heights related? You can say H1 over H2 would be equal to, G cancels out, right? It's just going to be D2 over D1. Okay? Or you can say H1 D1 equals H2 D2. So you can say that the pressure due to a column of liquid depends on the height and the density, but the height, the more dense it is, to have the same pressure, you're going to have more dense, lower density. Smaller height. Okay. You can say, see here, you can see that H1 D1 equals H2 D2. You've seen an equation similar to this before when you did the Boyles Law, P1 V1 equals P2 V2. One goes up, the other one goes down. Right? If you're dealing with the same pressure, height times density, we say would be inversely proportional. So, what's the pressure due to a vertical column of mercury 760 millimeters long? You should be able to do that. We'll just skip that. Okay. This is another conversion. Okay. Let's talk about pressure of a gas. All right. Traditional technique for measuring the pressure of a gas is to use a mercury column. Okay, so what you have here is an example of what's called a barometer. Inside this tube, you have a vacuum. There's nothing in there, right? And so what you could do to create that vacuum is you fill that tube with mercury and then invert it over a pool of mercury and then release. Okay? Now, the atmosphere, okay, air molecules colliding with that pool of mercury would exert a pressure that would force the mercury up into that column up to a height of about 76 centimeters. That's why one atmosphere is called, that's why we define 76 centimeters of mercury as one atmosphere. Okay? So the height of your mercury column then is a way we can measure the pressure due to the atmosphere. And so the pressure that the air molecules around us is exerting on us is called the barometric pressure or the atmospheric pressure. At sea level, this height is typically 760 millimeters. So we now define, that's why we define one atmosphere to be exactly 760 millimeters of mercury. Okay. Now, since atmospheric pressure actually varies, okay, to avoid confusion, it's preferable to call it barometric pressure because we use the unit 1 atmosphere to be exactly 760 millimeters of mercury. So the atmospheric pressure is not going to be exactly 760 millimeters of mercury. It varies depending on the weather and where you are. Okay. So it's preferable to just say barometric pressure instead of atmospheric pressure, so you don't confuse it with the unit that's atmosphere, which is defined to be exactly 760 millimeters of mercury. Now, what would be the pressure underwater at a depth of 50 meters? So let's say you're underwater, 50 meters deep, okay? And what would be the pressure that you would feel down there? Then what you need to do is calculate the pressure due to a column of water that's 50 meters. Okay, so that's 50 meters of water. Plus, you have to add to that the pressure due to the atmosphere, so whatever the barometric pressure is. Okay, so if you calculate the pressure due to water, what would it be? 50 meters. What's the conversion to meters of mercury? 1 meter of mercury is 13.6 meters of water. And then 1 meter of mercury is, okay, we're doing this in atmosphere, so let's just do atmosphere. So 1 atmosphere is 0.76 meters of mercury, right? 0.76 is 760 millimeters. So that gets rid of meters of mercury. And if you did that calculation, what would that give you? $50 divided by 13.6 times divided by 0.76. .84 bar atmospheres. 4.84 atmospheres. Okay. And your barometric pressure is 1 atmosphere, so the total pressure you'll experience down there is 5 atmospheres. Okay. By the way, 1 atmosphere is, in units you're more familiar with, is 14.7 pounds per square inch, right? PSI. So that's 5. It's almost 6 atmospheres. 6 times 15. 6 times 14.7 is about 6 times 15 is about 90 psi. That's how much pressure you'll experience down there if you're down there at 50 meters deep. So if you drop your watch down there, take your watch down there. Is your watch, and your watch is only rated. You look at your watch, your waterproof watch. You'll see at the back it has a rating in terms of how much water pressure it can, how much pressure it can withstand. So if your watch says 5 bars, that means if you take your watch down there, you won't be able to survive. Okay. Now, if you have a sample of a gas, you put it in a gas bulb, for example, you hook it up to what's called a manometer, and you can use that to measure the pressure of the gas. A manometer is really nothing more than a U-shaped tube that's filled with mercury. So this is mercury right here. And so in a closed-end manometer, this is closed. So that's the closed end right there. So what you have in a closed-end manometer is a vacuum up here. So whatever this height is, that's just the pressure of your gas. Now, if you open that up, what pressure would you be measuring? The pressure of the atmosphere. And so you're going to have a height of 76 centimeters of mercury or 760 millimeters of mercury. But if you connect that to a gas, then whatever that height is would be the pressure of your gas. So a gas is connected to a closed-end manometer. The difference in the mercury levels is 20 centimeters. What's the pressure of the gas in torr? So you have a closed-end manometer, and so this is your mercury. The difference in the height is 20 centimeters, and here's your gas over here. Okay. So what's your pressure? What's the pressure of your gas? It's just 20 centimeters of mercury times how's centimeter and millimeter related? 1 centimeter of mercury is 10 millimeters of mercury. And 1 millimeter of mercury is 1 torr. Okay. So that cancels that one. Millimeters of mercury cancels out. So that's how much? 20 times 10, 200 torr. That's 200 millimeters of mercury, so that's 200 torr. Okay. That's the pressure of the gas. Okay. Now note that this sketch right here shows this side is lower than this side. Why? Because what's the pressure over here? That's a vacuum, so that's 0. So you have 200 torr here, and you have 0 here. That's why you'll notice the gas is pushing harder on this side than it is on that side. Now, it's not really a perfect vacuum. There's a very, very small vapor there from mercury, so it's not exactly 0. So you still do have some gas in there, even though it's a vacuum. So we call that a high vacuum. But that would be negligible. The reason we use mercury is because mercury, one reason is it has a very low vapor pressure. Okay, so there's not going to be much pressure there from the mercury. All right. And for practical purposes, because atmospheric pressure, your mercury only goes up 76 centimeters, right? Now, if you had water for a barometer, what would happen to your water? How high would it go? 13.6 times higher, which is going to be at least around 30 feet. So that's going to be a very tall barometer. Okay. You can also use an open-end manometer for pressure measurement, and in those cases, your manometer is open to the atmosphere on one end, so you'll notice that's the open end right there. Okay. And the gas is hooked up to the other side. So one side is open to the atmosphere, and one side is connected to your gas. And in these cases, then, let's look at this scenario right here when the pressure of the gas is, would you say in this case on the left that the pressure of the gas is higher or lower than the atmospheric pressure, the barometric pressure? It's higher. It's pushing down farther, right, than the atmosphere. So that difference, we say, between the pressure of the gas and the barometric pressure, so you say the pressure of the gas is higher, so the difference between that and the barometric pressure is whatever this height is of the mercury column. So in this case, the pressure of the gas is the barometric pressure plus the height of the mercury pressure due to that height of mercury column. Now, in this scenario over here, what happens? What do you have? Your pressure of the gas is lower than the atmospheric pressure. So your pressure of the gas here is whatever the barometric pressure is, you subtract the height due to the column of mercury. Okay? So here's the problem. What's the pressure of the gas in the figure illustrated here? Okay, pressure of the gas is barometric pressure. Do we add H or subtract H? Subtract. The gas has less pressure than the atmospheric pressure. And so what would that be? What's our barometric pressure? Let's just assume we have 1 atmosphere. So what's 1 atmosphere in centimeters? About 76 centimeters mercury, minus our height is 55.0 centimeters. So what's 76 minus 55? 21 centimeters of mercury. So that's going to be 210 torr. Okay, 210 millimeters of mercury. Let's just make that homework. Okay. Slide 14. Let's talk about the ideal gas law now. Let's look at implications of the ideal gas law. If PV equals nRT, we said that's the ideal gas law, that's the equation that describes the behavior of gases at low pressure. Then if you have a fixed amount of gas, what do you have? N is constant, right? Fixed amount of gas, you're dealing with a constant number of moles. R is a constant. And T, if you're dealing with a gas at constant temperature, T is also constant. So you can say that PV then is going to be a constant, which is N, times another constant, which is R, times another constant, which is temperature. So you say that pressure times volume is a constant. Okay? If you're dealing with a fixed amount of gas at constant temperature. Now, if product of two things is a constant, we say that they are inversely proportional. If one goes up, the other has to go down. Right? So we can say that in one instance, whatever the pressure is, if let's say it's P1 and the volume is V1, in another instance, for as long as you're maintaining the number of moles of gas, you're maintaining the temperature, then the pressure at another instance, let's say P2 and V2, the product of P and V would be the same. So P1 V1 equals P2 V2 equals P3 V3. If you were to plot all those possible conditions on a diagram, on a chart, pressure versus volume, all the points that are at the same temperature for a fixed amount of gas will fall in a curve that looks like this. Okay? So you can see that if PV is equal to a constant, then pressure would just be equal to a constant over volume. So it's like a plot of y versus 1 over x. You get half a hyperbola. Okay? So at any point on this diagram, P1 times V1 equals P2 times V2 equals P3 times V3. Okay. Significance, we say, like I said, of this relationship is that this equation, whenever the product of two things is a constant, we say those two things are inversely proportional. If one goes up, the other one goes down. So let's say you have a sample of gas, initially at 1 atmosphere. You let it expand to 50 liters at constant temperature. What would be the final pressure? Then in this case, you say, okay, so if you want, you can start with PV equals nRT. Okay. Do you know the number of moles of gas? You have pressure and volume, but you don't know what the temperature is, right? And you don't know the number of moles of gas. Two equations in one unknown, so that equation is not going to work. But you do know the final volume is 50 liters, so and you know that number of moles and the temperature is constant, right? So you can say PV is a constant, so the initial pressure times the initial volume must be equal to the final pressure times the final volume, P2, V2. So this is what we would call a Boyles Law problem. So how do you solve for the final pressure? P1 V1 equals P2 V2. How do you solve for P2? P1 V1 over V2. Okay, I can say that's P1 times V1 over V2. And our P1 in this case is 1 atmosphere. And V1 over V2, 25.0 over 50.0. You can see you increase the volume, you're multiplying the original pressure by a factor less than 1. You expect the final pressure to drop. And so what's our final pressure going to be here? Half an atmosphere, 0.500 atmospheres. Okay, let's see. Which of these 4 graphs illustrates Boyles Law? A, B, C, D, or none of the above? C? Okay, Boyles Law says pressure times volume is a constant, right? So I can rewrite this. Let's say if I were to plot pressure versus 1 over volume. Now let's see. Pressure would be C times 1 over volume plus 0, right? I'm rearranging this equation. So if I plot this on my y-axis, and 1 over v is my x-axis, my slope is going to be C, and that C is equal to nRT. That's a positive slope, right? So this works, and my intercept is 0, so it goes to 0. So this looks good. What about this second one? What's wrong with this one? Your slope here is negative, right? And your intercept should also be 0, so that's wrong. How about the third one? 0 slope. What does a 0 slope mean? That means either n or t or both are 0, right? And so that's wrong. What about this one? That's a straight line. Positive slope, good slope, but the intercept is not 0, right? Assuming, of course, that the bottom left corner is the origin. So the best answer in this case would be A. All right, let's talk about Charles' law. Charles' law deals with the relationship between volume and temperature if you're dealing with a fixed amount of gas, a constant N, at constant pressure. So if you have PV equals nRT, you can rearrange that. Okay, PV equals nRT. Divide both sides by PT. That gives you pressure cancels out, temperature cancels out here. So you can say that V over T is equal to NR over P. And just collecting all the constants on one side. So I say V over T is a constant. Whenever the ratio of two things is a constant, we say those two things are directly proportional. Right? So whenever the ratio of two things are constant, they are directly proportional. So in other words, under these conditions, V1 over T1 would be equal to V2 over T2. So if you take your system from one condition, where it's got a volume and temperature, volume V1 and T1, you let one of those two change, volume or temperature. And as long as the pressure is constant, then that ratio of volume to temperature is going to be the same. Okay. Directly proportional simply means temperature goes up, volume goes up. That means if you heat a gas, what happens to it at constant pressure? It expands. If you cool a gas at constant pressure, it will contract. Okay, so gases expand when heated. That's provided the pressure is constant. Okay, and note here that the temperature we have to use here must be temperature in Kelvin, absolute temperature. So you have a sample of gas at 300 Kelvin heated to 600 Kelvin at constant pressure. What's the final volume of the gas? So here's a question that deals with how the volume of a gas depends on temperature. So you say V1 over T1 equals V2 over T2. Why can we say that? Because both of these are going to be equal to NR over P, right? And pressure is constant, fixed amount of gas. Nothing here to indicate that we're dealing with a change in the amount of gas. So V1 over T1 equals V2 over T2. How do I solve for the final volume of the gas? The final volume is V2. V2 equals V1 times T2 over T1. So what's my V1? 10 liters times T2, which is final temperature, 600 Kelvin, 600.0 Kelvin, and 300 Kelvin is my T1, my initial temperature. So Kelvin cancels out, and that gives me how much? This is 600 over 300, that's 2, so 10 times 2 is 20.0 liters. 3 sig figs, 4 sig figs, 4 sig figs, your answer should have 3 sig figs, 20.0 liters. Does that make sense? You double the temperature, you double the volume. That's what direct proportion means, right? If one changes, the other changes by the same factor. So if you triple one, the other also gets tripled. So you're essentially multiplying the original volume by a conversion factor, you might say, that is greater than 1 because the temperature went up. The temperature factor greater than 1. Hamilton's law. This relates pressure and temperature, and if you're dealing with a fixed amount of gas at constant volume. So if you put your gas in a rigid container, okay, the volume is fixed. Now that container may expand a little bit if you change the temperature, but for practical purposes, that expansion is not going to be that much. So you fix the volume, fixed amount of gas in there. Okay, so N is fixed, V is fixed. So you can rearrange PV equals nRT to say that P over T is a constant. And so again, you have a ratio of two things being equal to a constant. In this particular case, you have, you can see how the pressure is related to the temperature. What happens if you heat this gas? The pressure is going to, so if the temperature is going to go up, what happens to the pressure? It goes up. Okay, so we say pressure and absolute temperature are directly proportional. If you cool this gas, the pressure will go down. Okay, so if you are to plot pressure versus temperature, okay, at constant volume, the curve that you get is called an isotherm. Okay. Earlier we had an isotherm, right? Let's go back to an earlier slide when we plotted. This would be an example of an isotherm because temperature is constant. Every point on that curve represents the same temperature. What's another isotherm that we drew earlier? This one. Okay, every point on this curve corresponds to a point at the same temperature, so this is called an isotherm. So the word isotherm refers to all points on a curve that represent data at constant temperature, same temperature, isotherm. And isochore means same volume. Now what about same pressure? We didn't plot one. For Charles's law, what would the plot of volume versus temperature look like for Charles's law? Let's mention that. Volume is what? nR T over P, right? So we say that volume is equal to a constant times temperature. So if we call this our Y, and that's our X, what is nR over P? That's your slope. And what's your Y-intercept? 0. So if you plot volume versus temperature, you get a plot that is a straight line. What's the slope? The value of the slope? It's nR over P. And what would be your Y-intercept? Or if you were to extrapolate to 0 temperature, you get 0 volume. Okay? What do you call this curve right here? Where all the data points correspond to the same pressure. That's called an isobar. Okay? So data collected at the same temperature is an isotherm. Data collected at the same pressure would be an isobar. And the last one we talked about is an isochore. Data collected at constant volume. What would this plot look like? If I were to plot pressure versus temperature, what would I get? Let's rearrange this equation. Pressure equals nRT over V, right? So you're dealing with an isochore, fixed amount of gas. So this is going to be my Y. Pressure is my Y. Temperature is my X. What's my slope? nR over V. That's your slope. Now, is that going to be a positive slope, negative slope, or 0? Volume is always positive. Number of moles is always positive. R is a positive constant, so it's going to give you a positive slope. Now, what if I maintain the same volume and have more moles of gas? What would happen to my slope? My slope would be steeper, right? But all of those all of those curves, all of those isochores, so this would be for a different volume. Okay, if we're dealing with the same volume, you just change the number of moles. This would be the second curve right here. The steeper one would be for more moles of gas, right? If they have the same number of moles, which one would be a bigger volume? A or B? Which curve? Let's say I have more moles of gas, the same moles of gas in both cases. Which curve would represent an isochore corresponding to a bigger volume? Okay. Bigger volume would make a smaller slope, right? So B would be the isochore. If you have the same amount of gas, a bigger volume would have a less steep slope. Okay? Same thing for your isotherms. Remember, you have an isotherm that looks like that. Pressure versus pressure versus volume, right? What would happen if I were to raise the temperature? What would my isotherm look like? Would it be up here, or would it be down here? Oops. I'm not doing it. I'm not drawing it perfectly. Where would my isotherm be if I were to go to a higher temperature? Same amount of gas. What's PV? PV equals nRT, right? So for the same pressure and volume, for the same pressure, okay, and volume right here, at a higher temperature, what do you expect? Is the blue curve, is it going to be the blue curve or the black curve? Higher temperatures, you're going to need higher values of PV, right? So this is going to be higher temperature. This will be a lower temperature. So here's a question. Fixed volume container contains a gas at 300 Kelvin, 1 atmosphere. Temperature is increased to 600 Kelvin. Calculate the pressure. So fixed volume. So what law is applicable here? Boyle, Charles, or Amundsen? Amundsen. So P over T, P1 over T1 equals P2 over T2, which is going to be equal to NR over 3. In fact, you can solve for the volume, right? Can you? No, you can't. You don't know N. So since you don't know N, you can't solve for the volume. So, but you can solve for the final temperature, final pressure. So solving gas law problems. So what I've illustrated to you in the questions that I've shown you earlier is that you may not always have enough information to plug into PV equals nRT when dealing with gas law problems, but if that is the case, okay, a good strategy for solving these problems is to identify quantities that are being held constant, because usually you're dealing with cases where there's a change in one quantity. You figure out what the change in the other quantity is. So you have to be able to identify what are the constants that are either explicitly identified in the problem or implied in the problem. Okay, so you have constant moles and temperature, Boyles Law, P1 V1 equals P2 V2. Constant moles and pressure, an isobar, you have V1 over T1 equals V2 over T2. Which law is that? Charles's law. Constant temperature and pressure. So PV equals nRT. So if your pressure and temperature are constant, then you say V over N is equal to RT over P. Okay. So volume is directly proportional to the number of moles. So for a fixed pressure and temperature, you can use volume as a way of counting the amount of gas you have, counting the number of molecules that you have. So V1 over N1 equals V2 over N2. This is known as Avogadro's law. Okay. Which basically says the molar volume of a gas at a given temperature and pressure is constant. V over N, the ratio of volume to number of moles, that's called the molar volume. Any quantity expressed on a per mole basis is called molar whatever. Okay? So the molar mass is the mass per mole. Molar volume is volume per mole. Whatever the volume is, divide by the number of moles, you get the molar volume. So Avogadro's law says if temperature and pressure is constant, then the molar volume of your gas is a constant. Or you can also say that volume is directly proportional to the number of moles. Now, if you only have one constant, like only the amount of gas is fixed, and pressure, then you have pressure, volume, and temperature could change. 3 things that could change. Then you can say P1 V1 over T1 is equal to P2 V2 over T2. Why is that? P1 V1 over T1 equal to P2 V2 over T2. That's equal to what? That's just equal to NR, if N is constant. So that's known as a combined Gauss law. Okay. You can also say if volume and temperature is fixed, then P1 over N1 equals P2 over N2. And if volume and pressure is fixed, then N1 T1 equals N2 T2. Okay. Where am I? What time do we stop? 9. Oh, it's Tuesday. Okay, I'm still in the 3 AM time zone. So okay, so we'll continue this next time. Actually, we'll continue this